Right. Let's take a look now at the ideas associated with chemical reactions. How does one know a chemical reaction has occurred? Well, a gas can be produced. There's a permanent color change. Energy, such as heat, is released or absorbed. And a precipitate might form where a solid is produced from a mixture of liquids. Now you may recall that a few days ago I filled soap bubbles with methane gas and put a flame to it, and you can see the results here that got produced. Clearly this is a chemical reaction of the methane gas with oxygen. We discussed a few days later the use of methyl alcohol and other combustible materials as fuel for dragsters and funny callers, and I put some of the methyl alcohol in the Sparkletts bottle to make a flame. Was not as big as what you see here, of course. We talked about, if you want to, you can see these at the Pomona Raceway, usually in the spring. I did not include the tattoos that you normally see, but there you go. So the chemical reaction, what is it? It's a process whereby one substance or another is changed into a new substance. That's a chemical reaction. It's important to keep straight that you do not change one kind of atom into another. Rather, you are causing a rearrangement of atoms that make up the molecules or compounds to produce new rearranged molecules or compounds. The abbreviation Rxn is used for the chemical reaction. And when we write these out, one has a basic format. Those molecules that appear on the left are considered the reactants, and those that appear on the right are the resulting products from the chemical reaction. The arrow in the middle is where the rearranging process actually takes place. Now, we saw the dragster on the other slide with the flames coming out the pipes. That's a chemical reaction. We have octane fuel and oxygen, those are the reactants, entering the engine, and the resulting products is carbon dioxide and water. The chemical reaction is what takes place inside the engine, and the products are simply the result of that rearrangement. A precipitate is another kind of reaction. The ones earlier were combustion reactions that always involve oxygen. A precipitate is yet another kind of chemical reaction where two liquids are mixed and a solid is formed. And so a precipitate reaction is another type. Now, John Dalton, who's considered the father of modern chemistry, he really kind of suggested what went on during a chemical reaction. And as he postulated in the mid-1800s, is that if you took hydrogen gas, which is a molecule really, two hydrogens connected to a molecule to make hydrogen gas, and if you took oxygen gas, which are two oxygen atoms covalently bonded together, that he suggests what happened is the hydrogen gas molecules and the oxygen gas molecules, they fell apart. The atoms separated from each other. The covalent bonds fell apart, if you will. And all the atoms momentarily were all separate from each other. And in that state, they could undergo a rearrangement, allowing the formation of water. And so from his perspective, these molecules, the reactants, separated from each other, if you will, and recombined to make the molecules that were the products. Now this raises an interesting idea. Here we see the water and the bromine fluoride, and looking at it, you might suggest, right, the oxygen, the bromine, they could combine, and I now have a new product in the lower right. In fact, this does not happen because the lower right product is not stable. Now, John Dalton didn't know why, what the rules were that prevented the lower right product, but it's important to realize that not everything reacts with everything else, and that if, in fact, certain combination of molecules, like we see on the left, come together, it's possible that they will not successfully fall apart and rearrange so that the ending product is stable. And therefore, what you're looking at here is no reaction, because you can't get to products that are stable. And therefore, the molecules to begin with do not fall apart or do not react. So, if we have a successful chemical reaction, there are formats we follow that designate or indicate what that chemical reaction looks like. So there are three ways that we can show the hydrogen gas and the oxygen gas forming water, which was the reaction we saw previously. One way is to write it out. 2 hydrogen molecules, 1 oxygen molecule, those are the reactants, will produce 2 water molecules. We can use space-filling models. We have the 2 hydrogen gas and then the 1 oxygen gas producing the 2 waters. So you could see we use words, we can use space-filling models, and we can simply write it out symbolically. So all reactions have arrows, and the arrow is showing the direction that the reaction moves towards. It shows which molecules will start to fall apart, undergo rearrangement, and what molecules you wind up with on the other side. So the arrows go from reactant to product. However, then reactants here and the products there. However, as we will find out in several weeks from now, that reactions actually can also go in reverse. That sometimes the products, in fact, go backwards into the reactant state. And the arrow would indicate that. And I should get this to advance, but it doesn't. I'm not quite sure why. Sorry about that. Now we got it. So now I got products and reactants, but it goes the other direction. Again, we'll eventually arrive at what we refer to as equilibrium, which is actually you can have both taking place at the same time. For the next several weeks, however, in this class, you will work with the first item above, which is reactants on the left and the products are on the right. Now, during chemical reactions, the materials can be in certain states. As you can see here, Mg magnesium, you put in parentheses S because it's a solid in this particular reaction, and the O2 is a G gas, and then the MgO, magnesium oxide, is a solid. So when you write out chemical reactions, you indicate the state that they are in. Gases, L liquids, S solids, and aqueous, which means the material is dissolved in water. As we move forward, it needs to be indicated that the amount of solid of reactants and the amount of solid of the products does not have to match up. What I mean by that is, as you could see on the reaction given, the O2 is a gas, but on the right side products, there is no gas present. And that is not a violation, because you do not have to have the same states on one side as the other. In fact, often the chemical reaction causes changes in state. So the states have to be denoted, but they do not have to balance out on both sides. Now, a man by the name of Lavoisier was the first one who described a very important rule in chemistry, which is called the law of conservation of mass. And as you can see, what that simply says is You can't destroy or create out of nowhere mass. And what that means is that the total amount of reactant by weight has to equal the total mass of the product, and you cannot have it disappear. And Lavoisier in the 1789 was the one who worked it out. His wife was in fact his assistant, which didn't in the end work out well for them, for they were part of the aristocracy. And during the French Revolution, during the Reign of Terror, both him and his wife lost their head. But before that, he made significant contributions to chemistry, and the law of conservation of mass is among the most significant. So again, to restate it, a chemical reaction, the atoms don't change. They simply are rearranged. And this is an example of him doing his research in his laboratory. So how do I actually read a chemical reaction or a chemical equation? How do I verbally state it? We'll take this one here, and the answer is you would state 2 atoms of magnesium and the 1 molecule of O2 makes 2 formula units of magnesium oxide. And you use formula units because MgO is a type of salt. You can also say 2 moles of Mg, 1 mole of O2 makes 2 moles of MgO. The idea of a mole will in fact be taught within the next few days. Now, what you cannot say is you cannot say 2 grams, 1 gram, 2 grams. And the reason you cannot say that is because the weight of magnesium is not the same as the weight of an oxygen. So you cannot assign actual weights to these numbers. So, how does one make sure that the balancing of it all makes sense? In other words, how do you make sure the law of conservation of mass is obeyed? The answer is this, that 1 magnesium and 2 oxygen, and 1 magnesium and 1 oxygen. We need to balance this out. And what that means is, as the equation is currently written, a oxygen atom seems to have disappeared. We have 2 oxygen atoms on the left, but have only 1 oxygen atom on the right. And again, we spoke to it. The fact that there's gas on the left and the gas is gone on the right is not an issue. States of matter do not have to match up. But we cannot have an oxygen atom go missing. And so we have to now account for it. And that process is called balancing the equation. If we in fact have 2 magnesium oxides, we would now have 2 oxygens on the right and 2 on the left. We would need to add 2 magnesium atoms on the left. Let's take that back a little bit, sorry. So what this shows is we now have 2 magnesiums on the left, 2 magnesiums on the right. We have 2 oxygens and 2 oxygens. So we've conserved, during the reaction, we've conserved matter. We have conserved that the number of atoms on the left are the same as on the right. Let's take a look at this one. Propane is C3H8. It's going to react with oxygen to produce carbon dioxide and water and heat and light. Now, this slide illustrates the number of items. The number of carbon atoms on the left is the same as the number of carbon atoms on the right. 10 oxygens on the left. I've got a total of 10 oxygens on the right. Notice the oxygens have been divided up between 2 molecules. No problem. As long as all the oxygens are accounted for, however it got rearranged is fine. I also want to point out that in a chemical reaction, if heat is produced or light is produced, it is indicated on the reaction itself. It does not participate in the balancing of the reaction, but it is indeed accounted for since it does get released. What is the strategy to balancing chemical reactions? First, you write the correct formulas for the reactants and the correct formulas for the products. So let's write down the following. ethane reacts with oxygen to form carbon dioxide and water. Ethane is C2H6, oxygen is O2, carbon dioxide, CO2, and water. Now in this case, we're not going to indicate gaseous state, solid state. We will simply move straight to the balancing process. Now coefficients are the numbers placed in front of each molecule. So when we push a coefficient C2H6, we need to have two C2H6 molecules. You cannot simply add 2 more carbon and 6 more hydrogens. Because if you do, you changed the molecule itself. So we need to increase the number of molecules, the number of C2H6s, but you cannot change that molecule to some other one to account for the atoms. What we do now is we have to balance this. To balance it, we're going to start with carbon or hydrogen. And the reason you don't want to start with oxygen is because the oxygen exists in 2 different molecules in the product. So we have 2 there, 1 there. We have to multiply the CO2 by 2 to give me 2 carbon dioxides, which would give me 2 carbons. Again, notice it's written as a coefficient in front of the CO2. Now let's move on to hydrogen. There are 6 hydrogens on the left, 2 on the right. I cannot simply add a total of 6 to the H and create H6O. That molecule doesn't exist. So instead, I need 3 H2O molecules. Now we have to tackle the last one, which is oxygen. You'll notice there's 2 oxygen on the left, but there's 4 oxygen from CO2, 3 oxygen from the H2O. I have 7 oxygen currently on the right. So I have to now recalibrate so I can match my oxygens. And the method we're going to use is the 1 divided by halves. So we're going to multiply O2 by 7, because that's how many that I want, divided by 2, because that's how many I have on the reactant side. Now that's going to lead to a rather odd looking idea where I write a fraction 7 over 2 in front of the O2. But now what I'm going to do is I cannot have fractional molecules and I cannot have fractional atoms. It's always in whole numbers. So what I do is I multiply both sides by 2. I have to multiply all the molecules by 2 on both sides. That gives me 2 6-2H6. I get 7 O2s. I get 4 CO2s. I get 6 H2Os. And now all the atoms on both sides balance. To check that we have it all matched up, we could do the following. There's 4 carbons, 4 carbons. There's 12 hydrogen, 12 hydrogen. There's 14 oxygen, 14 oxygen. It all matches up. So this is the strategy we used to balance chemical reactions. We add coefficients to match them up. At this time, I'd like you to pause this. I'd like you to balance these reactions. So what I'm asking you to do is place numbers, if needed, in front of the N2, in front of the H2, or in front of the CaCO3s. You're going to figure out how to make sure that there's balance between the reactants and the products. So pause it now and try to solve it. Right. So you can go back and check to see if you were able to balance these 4 reactions. That was a hot presentation.